Okay, welcome back. So, studying 5.3 here, we're gonna look at a worked example. So you've got a second example of this, not just the one that's listed in your book. So we're gonna stick with glycolysis though, and we're gonna look at this reaction here, the conversion or the interconversion of dihydroxyacetone phosphate, or DHAP, to glyceraldehyde 3-phosphate down here by the enzyme triose phosphate isomerase. Now, this reaction is basically just shifting this phosphate around. There's some other stuff going on too, but that's all we're doing. We're just moving this phosphate around basically here. So let's take a look at this reaction. So I'm going to summarize the reaction here. G3P is interconverted with DHAP. So there is a back and forth here between G3P and dihydroxyacetone phosphate. So under standard conditions, remember there's 1 molar of product and 1 mole of substrate to start with. 1 molar substrate, 1 molar product to start with. The equilibrium constant for this reaction, DHAP being the product, G3P being the substrate, is 22.2. Always keep in mind what that actually means. That means for every molecule of G3P, there are 22.2 molecules of dihydroxyacetone phosphate. And so if we calculate the standard free energy change here, we can use this equation here, the negative universal gas constant times by the temperature under standard conditions, multiplied by the natural log of the equilibrium constant, and then when we multiply that all out, we end up with this value here, negative 1,835 calories per mole. So the reaction goes spontaneously to the right under these conditions, and so that means DHAP would accumulate. But the conditions in the cell aren't standard conditions. The starting conditions aren't 1 molar DHAP and 1 molar G3P, so we've got to take a look at how that affects things. So in cells, now these vary obviously under different conditions, nutritional conditions, but concentration of glyceraldehyde 3-phosphate is 1 micromolar, and the concentration of dihydroxyacetone phosphate is 10 micromolar. That means that for every molecule of G3P there are 10 DHAP, still keeping that in mind. So when you calculate the equilibrium constant for this, it's 10. So you already know that the equilibrium constant is greater than 1. So the products are going to predominate over the reactants, and delta G will still be negative. But as what we'll see, if we calculate this out, that we get delta G prime of negative 472 calories per mole. So we haven't changed the sign of the reaction, but we've changed the magnitude of the free energy change. Free energy is still being liberated here. You can change the sign of these things by changing the reaction, the concentrations of the products and substrates. I mean, if you just did 1/10 here, that would change this value down here significantly. Now, I've got to emphasize this, even though there's a negative free energy change here, and that tells you that this can happen spontaneously, this will not happen spontaneously in cells without an enzyme. So without triose phosphate isomerase, this reaction will not happen. So although the thermodynamics tell you that something can happen, that doesn't necessarily mean that biologically it will happen. And so you've always got to keep that in mind. So why then doesn't all the G3P in the cell accumulate as DHAP? Because DHAP formation is favored. The reaction would be driven towards forming DHAP, the product. The trick here is that the reaction is not in equilibrium. And the reaction is not in equilibrium because G3P, this molecule here, is constantly being removed by the reactions at the end of glycolysis. And so this actually drives the reaction towards glyceraldehyde 3-phosphate formation from DHAP production. Now, if you look at conditions where gluconeogenesis is occurring in cells, that's the formation of glucose. In that situation, dihydroxyacetone phosphate is being removed because we're basically driving these reactions backwards at the top of this diagram of glycolysis, so that we can make glucose to produce glycogen. And in that case, DHAP production would be favored. So this only really works when you understand what is biologically happening in the cell. So you've got to understand the cell biology and the biochemistry of the reactions, and you've got to put that in the context of what the cell is actually doing. If the cell is breaking down glucose to produce ATP in cellular respiration, then you've got to think about what is happening through these reactions and what is happening to the glyceraldehyde that we produced as a product of this interconversion. If this is constantly being removed, then this reaction is not at equilibrium, and that means the reaction will be driven towards G3P production. So thermodynamics, all these variables, delta G prime, delta G0 prime, equilibrium constant, the equilibrium constant under standard conditions of pH 7, all well and good. They tell us what can happen, but understanding what the cell is doing, that tells us what will happen. So keep that in mind as you think about these bioenergetics and some of these examples. That's it for the example. Next time we'll start taking a look at enzyme kinetics, and I'll see you for that shortly.